Ever wondered how the food you eat reacts inside your body? Or why vinegar tastes sour and soap feels slippery? Well, it all comes down to the subtle dance of chemistry, the heart of which beats with acids, bases, and salts. These aren't just fancy words thrown around in the science lab. They're everywhere, in the food we eat, the products we use, and even the air we breathe. Understanding acids, bases, and salts isn't just about passing an exam or impressing your peers. It's about understanding the world around us and how seemingly simple substances can have complex and far-reaching effects. From the sourness of lemons to the cleaning power of baking soda, acids, bases, and salts play a critical role in our daily lives. So, are you ready to dive into the fascinating world of acids, bases, and salts? Because we're about to take a journey that will change the way you see the world around you. Did you know metals react differently with acids and bases? Let's explore why. Picture a strip of zinc metal. Dip it into a beaker of hydrochloric acid. What happens? The acid reacts with the metal, producing zinc chloride and hydrogen gas. This is a general reaction where an acid reacts with a metal to produce a salt and hydrogen gas. Now, let's think about a base, like sodium hydroxide. If we try the same experiment with our strip of zinc, the reaction is a bit different. The sodium hydroxide reacts with the zinc to form sodium zincate and hydrogen gas. Here's the fascinating part. Not all metals react with bases. Some, like copper and silver, are unreactive with bases. Isn't that intriguing? Chemical reactions are all around us, happening every day. Understanding them helps us make sense of the world. So, it's not magic, it's chemistry. What happens when an acid and a base meet each other? Now, that's an interesting question. When an acid and a base cross paths, they don't just say hello and move on. No, they engage in a fascinating process called neutralization. But what does that mean? Well, in a neutralization reaction, an acid and a base combine to form a salt and water. This happens because the hydrogen ions from the acid react with the hydroxide ions from the base to produce water. At the same time, the remaining elements from the acid and base form a salt. It's like a chemically charged dance where the partners swap partners and create something new. And the result? It's usually less acidic or basic than the original substances. The term neutralization comes from this effect as the reaction leads to a more neutral pH level. So, when acids and bases meet, it's not always a fiery encounter. What happens when metallic oxides mix with acids? Well, let's delve into the details. When a metallic oxide comes into contact with an acid, a fascinating reaction occurs. This reaction produces a salt and water, a process known as a neutralization reaction. Let's consider a common example. The interaction between copper oxide, a metallic oxide, and hydrochloric acid. When these two react, they form copper chloride and water. You see, the copper oxide, being a base, neutralizes the hydrochloric acid's acidity, leading to the formation of a salt, copper chloride, and water. This isn't exclusive to copper oxide. Other metallic oxides, say iron oxide or zinc oxide, also react similarly with acids, producing respective salts and water. It's a fascinating dance of elements, isn't it? The world of chemistry is teeming with such interesting interactions, and this is just one of them. So, metallic oxides and acids do have quite a reaction. Now let's see what happens when non-metallic oxides meet a base. Non-metallic oxides, or acid anhydrides, are fascinating characters in the world of chemistry. They're typically gaseous or liquid compounds like carbon dioxide or sulfur dioxide. Now, what's intriguing is when these non-metallic oxides encounter a base, they react to form salt and water. For instance, let's take sulfur dioxide. When it reacts with a base like sodium hydroxide, it produces sodium sulfite and water. A simple yet elegant chemical dance, don't you think? Another example is carbon dioxide. It reacts with sodium hydroxide to form sodium carbonate and water. It's fascinating to see how these seemingly disparate substances come together to create something entirely new. These reactions highlight the acidic nature of non-metallic oxides. They also underscore the fact that chemistry is a dynamic and endlessly surprising field, where elements and compounds transform and interact in the most unexpected ways. Interesting, isn't it, how non-metallic oxides react with bases? Ever wondered what happens when you dissolve an acid or a base in water? Well, when acids dissolve in water, they produce hydrogen ions, which are simply protons. This is because acids are proton donors. On the other hand, When bases dissolve in water, they produce hydroxide ions. Bases are proton acceptors, and they can readily combine with the hydrogen ions produced by acids. Let's delve a bit deeper. In a water solution, an acid donates a proton to a water molecule to form a hydronium ion. Bases, however, accept a proton from a water molecule, resulting in a hydroxide ion. The fascinating part is that water can act both as an acid and a base. This is why water is often referred to as an amphoteric substance, being able to donate and accept protons. It's all a delicate balance, but one that's crucial to many chemical reactions and processes. So water does change the game for acids and bases. Have you heard about pH and how it's used to measure acidity and alkalinity? Well, let's delve into it. pH is a logarithmic scale used to specify the acidity or alkalinity of an aqueous solution. It's a fascinating concept that ranges from 0 to 14. On this scale, a solution with a pH less than 7 is acidic. Imagine biting into a juicy lemon or sipping a tangy vinegar. These have a low pH. On the other hand, a solution with a pH greater than 7 is basic or alkaline. Think of the bitterness of baking soda or the sharp taste of soap. Now, how do we measure this pH? That's where indicators come into play. These are substances that change color based on the pH of the solution they're in. For instance, litmus turns red in acidic solutions and blue in basic ones. So, pH isn't just a fancy term, it's a very useful measure. Why should we care about pH in our everyday lives? Well, pH is more than just a concept in chemistry. It has a profound impact on our daily lives, from health to cleaning and even gardening. When it comes to health, our body works best when it's at a specific pH level, typically around 7.4. This is the pH level of our blood, and maintaining it is crucial for our well-being. Imbalances can lead to health problems like muscle pain, fatigue, and even serious conditions such as diabetes. In cleaning, different pH levels are used to tackle different types of dirt. Alkaline cleaners, for instance, are great for breaking down oils and fats, while acidic cleaners are more effective against rust and mineral deposits. Even in gardening, pH plays a role. Soil pH affects the availability of nutrients to plants. Some plants prefer acidic soil, while others thrive in more alkaline conditions. So, pH does play a crucial role in our lives. Do you know there are different types of salts and they have different pH values? Let's dive into the fascinating world of salts. Salts, a product of the reaction between an acid and a base, are more than just the table salt we know. They form a large family, each with its unique characteristics. We have common salt, or sodium chloride, that we use in cooking. Then there's Epsom salt, a magnesium sulfate known for its therapeutic properties. And let's not forget baking soda, a bicarbonate salt used in cooking and cleaning. But here's the kicker. Each of these salts has a different pH level. While table salt is neutral with a pH of 7, Epsom salt is slightly acidic, and baking soda is basic. The pH of a salt depends on the acid and base that formed it. This means, despite being part of the same family, each salt has a unique identity, a unique pH. So not all salts are created equal. Did you know that common salt is not so common after all? Yes, you heard it right. When we look at it through the lens of chemistry, common salt or sodium chloride is a gateway to a host of useful chemicals. And the key to unlocking these chemicals is the Chlor-Alkali process. So what is the Chlor-Alkali process? It's a method used to produce chlorine, hydrogen, and sodium hydroxide, three very important chemicals, from salt. It involves passing an electric current through a solution of brine, which is just a fancy name for very salty water. The electricity breaks down the salt into its component ions, which then recombine in various ways to form our desired products. Chlorine, for instance, is used in water treatment and in the production of PVC. Sodium hydroxide, also known as caustic soda, has numerous industrial applications, including paper manufacturing. So common salt does have some uncommon uses. Ever wondered how common household items like bleaching powder and baking soda are made? Well, let's dive into it. Bleaching powder, also known as calcium hypochlorite, is made by reacting chlorine with dry slaked lime. It's widely used for water treatment and as a bleaching agent. Baking soda, or sodium bicarbonate, is made by a simple reaction between carbon dioxide and a solution of sodium carbonate. It's a key ingredient in baking and also serves as a great cleaning agent. Next, Washing soda, or sodium carbonate, is made by heating baking soda, which leads to water and carbon dioxide being driven off. It's a common component in laundry detergents. Lastly, plaster of Paris is made by heating gypsum at a specific temperature, and it's used for making statues and casts. So, the chemistry behind these everyday items is pretty amazing, isn't it?